Welcome to this evening's public forum as part of the third Southern Hemisphere Summer Space Programme. My name's Andrew Parfitt and I'm actually Deputy Vice-Chancellor Academic at the University of Newcastle. You may wonder why the Deputy Vice-Chancellor Academic at the University of Newcastle is chairing the panel here. Up until about a month and a half ago, I was Pro-Vice-Chancellor for Information Technology, Engineering and Environment here at the University of South Australia. So I have a strong affection for this university, but also an involvement from the beginnings of this summer space programme. Let me just start tonight by acknowledging that the presentation takes place on the land of the Kaurna people, and we acknowledge their heritage and their traditions and their ownership of the land. So I will give a brief presentation in a moment about the Australian Space Research Programme before we showcase 4 of the projects that are being funded under the programme. But the lay of this evening will be that after I've spoken a little bit about the programme and how it aligns to Australia's space initiatives, if you like, I'll introduce each of the speakers in turn to give their presentations. And then we'll have a period afterwards where we can have a discussion around individual aspects of the various projects, how they align, how they fit into the overall scheme of things, and we'll go for about half an hour after that. And then afterwards, you're all invited to join us for drinks and refreshments up in the Kerry Packer Gallery at the back. Just get rid of the security alert. And let me outline for you the parameters of the programme. Many of you will be aware of Australia's involvement in space for many decades, right back in fact to the origins of the space age in some ways. I think we were the 4th country to launch a satellite from our soil. Had a rather checkered history since then in many ways, stop and start, and in spite of acknowledging perhaps the reliance that Australia has on space technologies and space services, there hasn't been a lot of activity in recent times outside of the astronomy area where we have a lot of expertise, and Harvey might sort of mention that in passing later on as the recent director of the Research School of Astronomy and Astrophysics at the ANU. But apart from the astronomy activities, there's been little in the terms of space science and technology until a Senate inquiry, one of several Senate inquiries of several different government interventions, if you like, over the past 2 decades, finally came up with a document which was curiously titled Lost in Space. That document highlighted that there were significant gaps in Australia's capability to engage effectively in the space community internationally, as well as developing capabilities of our own. And so the Australian Space Research Programme was created along with the Space Policy Unit of the Australian Government to coordinate activities associated mainly with civilian space. Now, in the scheme of things, the allocation of funding to the programme is relatively modest. $40 million was established in October 2009. It was started with all the projects scheduled to complete by July 2013. So this is kind of concertina of projects with shorter duration as they were funded later on in the actual programme. And they were funded under 2 streams: space education development programmes, recognising the importance of skills development, and also to some extent outreach, and Martin West will talk a little bit about outreach activities later on, but also space research and innovation programs. Now, I said earlier $40 million isn't much, and I guess it's a bit trite to say this, but Australia does have a history of doing quite a lot with a relatively small amount of money. And that's probably one of the attributes of our science community that position ourselves really well when you look at things like citation metrics and so forth, from how you measure the quality of the science that comes out of Australia's universities and research institutions. Punch above its weight, I think, is the words that are used quite often. And the reality is that's done because you convert relatively small amounts of money into really good outcomes. So the objective, as I said, was to develop some niche space capabilities and supporting some research, innovation and skills in areas of national significance or excellence. Now, I'll come to the last bit later on, just when I finish up this brief introduction, because at the same time that this program was put in place, Australia was also setting about developing the principles by which it would implement a space policy. Curiously, the policy still hasn't been released, but the last funding of the program has. So we'll see at the end of this whether or not there is a sort of an alignment with the general principles that the policy might follow. So I'm only going to flick through these and mention in detail so you can get a flavour for the sorts of projects that were funded. And they were chosen by an independent panel, including international experts that came and, for each of the 4 rounds, chose to invest various organisations, including not only universities but companies as well. And we have Andrew Clark here from VIPAC, from a company that was funded to do some of this research as well. So there were partnerships. Each of the projects had to have international partners as well as local partners, and so they're each consortium. So I've only mentioned the lead agency in each of these. The first one, which was a Stream A, you remember that's the education one, was Pathways to Space. It essentially sets up a Mars yard in the Powerhouse Museum in Sydney, which enables school kids to come in and learn about autonomous vehicles. It's basically to promote science to school students. Stream B in round 1, the project Platform Technologies for Space, Atmosphere and Climate, funded to RMIT in Melbourne, Royal Melbourne Institute of Technology. It's essentially about modelling the effect of the atmosphere really on space services that were delivered either for positioning and timing and navigation or for Earth observation. So it involves a lot of processing work on the sorts of platforms and the technologies that are used for climate monitoring as one example. Round 1 also had a project on scramjets. Australia has had a long connection with space propulsion in one form or another, and the scramjet project up at the University of Queensland was funded. And the final project in the first round was Antarctic broadband. If you think about it, it's pretty difficult to provide broadband services from geostationary satellites to the Antarctic and the Arctic, but there's quite a lot of activity that goes down on at the South Pole. And so this was to provide facility by means of Earth orbiting satellites rather than geostationary satellites to actually provide data collection capability and communication capability for the enormous range of science that's taking place in Antarctica. Then round 2 came along, and another Stream B project, synthetic aperture radar formation flying. SAR satellites have been of interest to Australia primarily because of their complementary capability to other forms of Earth observation, particularly optical Earth observation satellites, and their capacity for the sorts of imaging that you can use for disaster management, and that this project was looking at how you could get a formation of small satellites producing a suitable aperture to get good resolution for disaster management from radar from space. Now, I could give a 30-minute presentation on the Southern Hemisphere Summer Space Program, and many of you sitting here should give a cheer for the Australian Space Research Program, because the funding that provides scholarship support actually came from the Australian Space Research Program. So this was actually supported in the second round and established very quickly afterwards, and hopefully has a bright future. It's based on a long-term collaborative partnership between this university and the International Space University. And I can see Renee Osterlink here, who's President of the Board of Governors from ISU. Stream B, round 2, laser tracking of space debris. Australia has a responsibility for ensuring that the space environment is safe to use. And given that we're in the south, geography plays an important part of here, plus historically a significant investment in technologies for tracking space debris very accurately using lasers. And this was awarded to the company that is a world expert in this area, EOS Space Systems Proprietary Limited, based in Canberra. And then the GRACE follow-on mission, that's Gravity Something and Climate and Environment Satellite, basically looks at monitoring, to create an instrument as part of an international partnership to monitor movements in the geophysical environment, particularly things like water for Australia, water movements and the water table of Australia. The first mission was very successful in that this is to participate in an international collaboration to create a follow-on mission and an instrument. And the ANU is involved in that one, I think, as the lead. Round 3. Place and Space. It's a Stream A project, Perspectives in Earth Observation. This is to get students and, more importantly, I think, teachers involved in understanding what science and technology can do and get them excited by space. Flinders University has a long-established aerospace activity in terms of Earth observation, and this is a good synergy because you can actually demonstrate some of this on the aircraft there. Martin will talk about more about this later on. Again, this is designed to stimulate students to be interested in pathways that will lead them to develop skills that are of national interest. Landsat, many of you will know, has been a significant sequence of satellites over many years, creating an enormous amount of data. And the second project funded in round 3 was to actually develop the infrastructure that's required to mine all of that data for new information and to provide a systematic international framework by which you can maximise the information that we've acquired over many years from the Landsat sequence of satellites. And finally, another one that was funded at UniSA, Bill Cowley, we'll talk about that later on, is a space-based national wireless sensor network aimed particularly at multiple sensors on over a large geographical area, bidirectional sensors to be able to take environmental measurements or a whole variety of other measurements that might be possible, acquire them via satellite cheaply and deliver that information to customers. And the final round, round 4, the education project in this round was essentially a tertiary education project, actually the first tertiary education project that was funded, mainly a master's program based on expertise in satellite engineering at the University of New South Wales. Then Stream B, a plasma thruster project, also at the Australian National University. The plasma thruster project, the plasma thruster work has been going on for many years. It is quite unique here in the terms of the sorts of technology that's being used, but it's a very economical way of being able to both create deep space propulsion as well as potentially being able to position satellites. And finally, also one that we'll showcase tonight, a Stream B project, some VIPAC engineers and scientists to create a greenhouse gas monitor to understand the flow of greenhouse gas and the sources and sinks in the environment attached with climate change. So you can see an enormous range of projects that were funded, touching technologies, applications, interventions, if you like, to make use of information that we've already got, plus the significant education activity work that was done. So quite a comprehensive program for $40 million, and we'll hear some of the outcomes at the stage they are at the moment. Now, I put this up just to finish. Australian Space Policy Principles. It's actually gone through a few iterations. When it was released, it was called the Australian Space Industry Policy Principles, and I think it's now known as the Australian Satellite Utilisation Policy Principles. You can see that sensitivity still exists around putting big bucks into space. And in spite of the fact that it may well be called Satellite Utilisation Policy, if you look at the 7 objectives that are on the board, you can see, I hope, that the projects that were funded through the ASRP align to a pretty good degree with the principles that are being set out and hopefully will be articulated in the near future in an actual policy as opposed to just a consultation document that's out at the moment. It remains to be seen whether the Australian Space Research Program actually does extend and underpin the implementation of these policies. We hope that it might. But whatever it does, what it has provided is some fantastic collaborations, some fantastic international connections, probably some very good science, and we'll hear about that later on. And hopefully in due course we'll be able to hear more of the outcomes from more of the programs. We have 4 tonight, so I'll launch into each of those 4 projects that have been funded. And the first one will be presented by Professor Harvey Butcher, Emeritus Professor now Harvey Butcher, formerly the Director of the Research School of Astronomy and Astrophysics at the Australian National University, who I should point out is also a sponsor of this evening's event. So thanks, Harvey, for ANU supporting this, and indeed for ANU's strong support for the summer program. It's much appreciated that we have such fantastic national collaboration in this activity. Harvey's an astronomer, don't hold that against him. He's a BSc in astrophysics from Caltech and a PhD in astronomy from ANU. He's worked in the US and internationally, extended period of time in the Netherlands, where he was director of the Netherlands Foundation for Research in Astronomy. And he's made significant achievements to radio astronomy technology, particularly in the implementation of the low-frequency adaptive array telescope, which was a pathfinder type of implementation for the square kilometre array. He was director at ANU of the RSAA from 2007 and 2013, and is now enjoying some quiet research time, I understand it. Please make him welcome.
Thank you, Andrew. I'd like to tell you a little bit about the ASRP projects that are going on at Mount Stromlo. And I have to begin by acknowledging that astronomy is excluded from the ASRP program. Astronomers have been very well funded in the past decades here in Australia. We very much want to use satellites. We're very much involved in the Hubble Space Telescope and other astronomical satellites. We're also very much involved in building the next generation of giant ground-based telescopes. So we want to use satellites. The ASRP doesn't let us in, but on the other hand, the engineering protocols, the kinds of facilities we need to do our astronomy are very similar to what one needs for building small satellites. So we're very much involved in this program, even though we're not supposed to be. So let me say a few background remarks, just so you know where I'm coming from. The Mount Stromlo Observatory was burned down almost entirely in 2003. So that was terrible, and it's caused quite some years of recovery. The silver lining in this is that we could rebuild our engineering facilities to include space engineering, which it didn't very much previously. So that's the good part of having your facility burned down. We're leveraging the investments in astronomy. We've got an awful lot of money to participate in a $1 billion international giant ground-based telescope called the Giant Magellan Telescope. So we're very heavily involved in the technologies for building advanced telescopes. And in particular, we needed a laboratory that would allow us to build one of the scientific instruments and to build the kind of optics you need for correcting for the blurring in the Earth's atmosphere. So those are the kinds of technologies that we really require. And it turns out they're very much similar to what one needs for small satellites. So we're able to build a laboratory which can do both. Now, the ASRP projects also brought some investment, and I'll say a few words about the kinds of facilities that we've been able to build at Mount Stromlo through the ASRP program as well. So what we have is a $30 million facility for assembling, integration, and testing of small satellites. It's nationally accessible. We certainly hope there'll be a follow-on to the ASRP-1 program, and we hope that people who want to build things and do things will make use of our facilities. Right now we're supporting, because we're not allowed to take the lead in, but we're supporting 5 ASRP projects, and I'll say a few words about that in a moment, as well as some other international projects. Okay, so this is the facility that we managed to build. It's called the Advanced Instrumentation and Technology Center, so it can evolve into almost anything that uses technology, including space. It is funded partly from insurance money from the fire, partly from this Giant Magellan Telescope grant, and partly from the ASRP. I'm not going to go in great detail to this particular diagram, but what you see here is that There are two wings to a building. The wings hold offices and laboratories, and there's some quite large spaces available in the middle for building big things, test facilities and so on. And so what I'd like to do is just talk about some of the facilities that are being implemented and should go online this year. So I'll start off with over on the left-hand side, there's quite a large clean room, class 10,000 in the old way of talking about these things. And that's gone into operation, so we can accept and host groups that want to build fairly large things. Maybe they want to have a small satellite, but they need a test facility in the same area or something like that. So this is quite a unique facility, at least in the civilian world here in Australia. The other one is just a large hall. It's for integrating things. We thought we would be building giant Magellan telescope facilities, and the Giant Magellan telescope is a gigantic telescope, 25 meters across, the main collecting mirror, and a couple times that large. So the instruments and everything is very big. Turns out we've been very clever and we can build something somewhat smaller than that. So we have this fantastically large assembly hall that people can use for building quite large things. It's relatively clean, relatively temperature controlled, but it's not a clean room. The other thing which, one other thing which is going in derives from the Australian Plasma Thruster Project. The group in physics at the ANU has come up, as Andrew said, with a very clever way to build plasma thrusters, and they need to demonstrate this in the lab before they can get a launch. They think they can probably get a launch in 2015 or 2016 if they can demonstrate the successful operation on the ground. So we're putting in a thermal vacuum space simulator. It's a very interesting tank. It's got lots of windows in it. You can crank the temperature down to 170 degrees below zero and up to 150 degrees above zero. You can make a vacuum very much like in space. You can put an engine in there, plasma engine, or you can put equipment in there that you want to see how it might behave in space. It's a very large tank, and you can put a small car in this tank if you wanted to launch it. So that gives you an idea of how large it is, and you can put quite significant satellites and things in there. Other things that are being implemented are a vibration table, a programmable table that allows you to test your mechanical models of your satellite, the modal analysis. We're aiming at right now for satellites, small satellites, CubeSats and so on, up to about 25 kilograms, but it's able to handle up to 250 kilograms, which is small satellites, a significant satellite. So we think there's a market for that, and that'll be available from later this year. When you build something that you want to send into space, you have to make sure that the electronics don't disturb the other systems on the platform. So we need an electromagnetic compatibility test facility. And so that's going in. We'll be able to make sure that whatever electronics, circuit boards, and so on get made aren't going to cause any trouble to anybody else on the satellite platform that they're going to be on. We have a test facility for mass properties, so you can actually measure the center of mass, the moment of inertia, and things that you need to build a control system to be able to operate these things. We have a spectacular laser lab together with the EOS Space Systems Company. Andrew mentioned these are the people that shoot lasers up to measure the orbits of satellites. They shoot a strong laser up, and they can take a little piece of paint or a piece of frozen rocket fuel or something, a couple centimeters in size, and measure its orbit quite accurately. So this is a unique facility, and it's being developed in two directions. One is to be able to have enough power in your laser to move objects in their orbits, so that's a powerful laser. And also to have what the astronomers call adaptive optics, to take out the distorting effects of the Earth's atmosphere, so you can pinpoint smaller and smaller bits of space debris and actually put your laser right on them. So that's a very interesting development. We also have an optics test laboratory, which is clean. It's quite large. It sits on bedrock, and so it's quite good for testing interferometric optics and things like that. Next to that AITC building, we also have, of course, a machine shop, and the Antarctic Broadband Project brought along a ground station, a UHF uplink and S-band downlink antennas, and so we're able to communicate with small satellites that make use of these facilities, and indeed I expect that's going to be a much more interesting, or very interesting facility in the future, as well as more and more CubeSats and other small satellites come online. So that gives you a bit of an idea of what's being implemented. Design offices, we have a team of about 35 people that have experience in the space engineering area. We've adopted the European Cooperation for Space Standardization systems engineering protocols, so we can interact with people around the world. We think that the goal, and we think we should achieve that goal this year, is to be able to make available a one-stop shop for CubeSats, nanosats, and small satellites. So that's where we're going on the engineering side, if you will. The 5 ASRP projects that we're supporting, I'll just list here. I won't go into a great deal of detail. The space debris project of the EOS Space Systems Company is something we're working very closely on, both on the control system side, on the laser development side, and also on the adaptive optics. So this is something which the astronomers need because they want really sharp pictures of the stars, and space debris people want because they want to be able to measure the space debris very, very accurately. The market for this is to be able to tell telecommunications companies and the Defense Department when one of their satellites is going to get hit by a piece of space debris. And of course, if that's going to happen in the next week or so, you can charge any amount of money, and they'll be able to pay it. So the market looks really good for that. The Antarctic Broadband Project to bring broadband internet to Antarctic researchers has brought with it the ground station for us. It's had a prototype satellite, didn't get launched, but showed that it should be able to work just fine. And now people are in the middle of trying to get venture capital to be able to actually launch these satellites. The GRACE missions have to do with 2 satellites which are in orbit, and there's a metrology system. The current GRACE, GRACE 1, has a metrology system that measures the distance between these 2 satellites using microwaves. And what you measure as it goes around the Earth is the lumpiness in the Earth's gravitational field. What you can do, and what the people in Earth sciences have shown, is that you can actually see the water in the Murray-Darling Basin move down towards South Australia. You see the water not only on the surface but also underground. That kind of sensitivity is there, and the algorithms for how you do that are now worked out. So the next stage for GRACE follow-on, the GRACE 2 mission, is to improve the metrology between the 2 satellites so that you can measure smaller changes in the gravitational field. So we're in the middle of doing not an improved microwave metrology system, but a laser metrology system. And it'll give a factor of 50 improvement in the ability to measure the gravitational field as these satellites go around the Earth. It's scheduled for a 2015 launch, so it's getting very exciting. I'm not going to say anything about greenhouse gas monitor because Andrew's going to talk about that. The plasma thruster I've mentioned a little bit about. It's an engine which can be used, put on satellites. It can use almost any kind of fuel. If you want to use grape juice, you can use it. It's a very strange kind of a phenomenon. You ionize particles and shoot them out the back in a very clever way. And it'll be used for deorbiting satellites or moving them in their orbits. It'll be used for deep space probes and things like that, which require not large thrust, but constant thrust over a very long period of time. So that's something we're in the middle of actually building all the facilities to test this and so on. Okay, we're also, because it's the ANU, it's a research, education, and training facility. So we have programs in postgraduate research. The one that's closest to the ASRP is a project called BRIGHT, which is a constellation of 6 nanosats, CubeSats actually, from Canada, Austria, and Poland. And this constellation of satellites will look at bright stars to see when planets might go in front of these bright stars. And you'll see the star dim a little bit, like the transit of Venus that we had a few months ago. There are a number of such satellites and ground-based systems looking for these kind of transits of exoplanets, planets around other stars. But they mostly are measuring rather faint stars. And if you want to be able to study the atmospheres of the planets, you need to find them around bright stars. So this constellation of satellites called BRIGHT is supposed to find all of the transiting planets around other stars where the stars are bright. So that'll be interesting to see how that goes. Undergraduate projects, we have a number of. We're looking at a model, if you will, where the education is mostly at other universities, UniSA, UNSW, wherever, and we perform a kind of finishing school where you come and you actually do projects with hands-on exercises and things. We have a satellite toolkit which allows you to put together a satellite mission and see how it might go. So that's for undergraduates. For short courses, we've been giving courses to government, telling them what does it mean to do satellites in space, what do you have to pay attention to, and so on. We think this will complement in the long run the ISU and this summer program. Interns, we have right now a spectacular intern program. Even though there's only 4 interns, they've turned out to do wonderful things. 2 from ANU, 1 from UNSW, and 1 from Sydney. One of them is doing small satellites for astronomy, seeing what can be done with CubeSats and very small satellites. So I'm very interested in that. One's worried about radiation testing. I didn't mention radiation testing as something you have to worry about if satellites going through the radiation belts, but we're not going to do any of that. But if you do need to do radiation testing, we'd like to be able to do it here in Australia. And so we're setting up the kinds of collaborations with nuclear physicists and ANSTO and so on to make that possible. And we've got 2 students working on ground station networks around the country, trying to set up a network to where small satellites, we can receive the data, we can communicate with them, we can join international networks which have launched CubeSats and actually benefit from the work that other people have done. The interns have spent 3 days with the Space Policy Unit, with EOS Space Systems, and with Aerospace Concepts to get the government and the industry points of view. So that's been very successful, and I'm sure that's going to continue in the future. We have a grant to do exchanges with Japanese high school teachers. I'm not going to go into that. But we do also have a program called Kibo ABC, and that gives students access to the Japanese Kibo module on the International Space Station. So high school students can actually formulate projects, things to do in zero gravity and so on. Ultimately, we hope that we'll be able to launch CubeSats from the International Space Station, and we can be part of that. The future at Mount Stromlo, assuming that we don't participate formally in the coming ASRP, or ASRP 2, what we do in any case want to have is an integrated center where we have our academics, we have our engineering, our R&D, we have spectacularly good facilities, not only for our astronomy, but also for space activities. We're very interested in hosting R&D groups from commercial companies. I haven't said anything about our public outreach, but of course we very much would like to have a astronomy and space center up at Mount Stromlo, working on that. But let me just say something about companies. We're very interested in a model in which high-tech companies are interested in getting into the kinds of technologies we're interested in. Maybe they're able to co-invest a little bit, and we'll be able to host them, and they can come with a team and work with us for as many months as they need. So I'll stop there. The person that people should contact if you're interested in any of the things which I've said is Dr. Naomi Mathers. She's joined us recently from the VSEC school in Melbourne, and is involved in setting up this program. So I'll stop there. Thank you.
Thank you, Harvey. The next speaker is Professor Bill Cowley, who will be known to many people in the summer school. He is a local boy, received his PhD and bachelor's degrees from the University of Adelaide. He's worked for the Defence Science and Technology Organisation, but has spent over 20 years in communications signal processing. He was the Satellite Communications Program Leader in the Cooperative Research Centre for Satellite Systems some years ago, and was for a time the Director of the Institute for Telecommunications Research. He's currently Communications Signal Processing Professor at ITR and Leader of the High-Speed Data Communications Research Sector at ITR. Bill's had a long connection with the International Space University since the summer program in Australia during winter. That was kind of a curious event, but in 2004 he's lectured many times with the ISU's programs. So Bill, thank you very much.
Yes, good evening. I'd like to tell you about our project, the Global Sensor Network, ASRP project from round 3 that Andrew mentioned beforehand. A project which are running at the University of South Australia, my institute, ITR, the Institute for Telecommunications Research, is leading this consortium. We have a Canadian company or a global company based in Canada, ComDev, and we have a number of other Australian organisations, and I'll mention some of those as we go through this presentation. So let me try to explain what this is all about, this project. Satellites are very good at sensing some things that are happening on the Earth's surface, but there's no substitute in many instances for actually taking those measurements on the surface of the Earth itself. We actually need to do that. For example, if you want to measure gas pressure or oil flow in a very remote part of Australia, you need to have a sensor on the Earth's surface which can undertake those readings. And there are many places, for example in this country, which don't have access to 3G or conventional communications infrastructure, so you'll need to use satellites to actually get that information up. In fact, Sage Automation, one of our partners, tell us that surprisingly the standard way of doing this at the moment in Australia is for a chap to drive around to the different sites and plug in his laptop and download data, and that's pretty surprising in this day and age, but that's what happens. The Great Barrier Reef, AIMS, the Australian Institute for Marine Science, are one of our group, and they're interested in, for example, global warming events, measuring characteristics of the ocean, including the temperature. And from the inner reef, you can do that with 3G systems, but from the outer reef, it's not possible to do that. And of course, you need to use satellites. Australia has a large area of land, of course, for grazing and arable land. And so there's many cases here where you want to measure soil properties or other variables, which of course you can do by satellite. In fact, just on the ABC News this morning, I heard another application that would suit our particular service, and that is that in South Australia there's a group of feral goats, according to the ABC News, which are causing sufficient damage and which need to be neutralised. And what they're going to do is they're going to put some Judas goats with satellite trackers into the outback areas, who will team up with the feral goat population, allow hunters to find the location of these, and the side effect of this is that the lions at Monarto Zoo need to be fed, and according to the news, that's where the lions will be fed from, using the proceeds of that exercise. Anyway, that's an example of animal tracking. Now, the point is that there are many applications where we need to have this remote sensing. Many of these applications don't need instantaneous reporting of the data. They need a couple of times a day. This is suited to satellite collection, maybe to LEO satellite orbits. So that's what we're looking at in our project. Of course, there's a bunch of national security and monitoring and surveillance type applications as well that one could envisage. In fact, a large number of applications, some of them are listed here, but I've said quite enough about that, and I need to carry on. So that's the motivation. Now, if we look at the specifications of the type of system that we'd like to build, we want to handle very large numbers of low-cost terminals. Okay, so globally up to millions. We're looking at a modest overall cost, so not geostationary satellites, but microsatellites or small satellites. I'll say in a minute, we're looking at various types of applications which will involve both one-way and two-way communication between the Earth and the satellite. And nowadays we're often talking about software-defined radio systems where we can flexibly change the operation, and we'll see from the next couple of slides that it's most important that we can do that in the system that we're proposing. Of course, we've talked about the global nature of it. Some of these things, of course, there are systems out there which will collect data, but none that tick all of the boxes that I've listed here. And in particular, I guess it's the very large number of terminals which we're particularly focusing on. Good. So just a word about the Canadian connection here. ComDev, it involves our major partner ComDev that design and manufacture space equipment, but it's more than just that. There have been a number of discussions with the Canadian Space Agency. The type of service that we're proposing here would be very well suited to applications in many countries, and particularly in Canada. Despite the climatic differences, there are a large number of similarities between our two countries, and so there's been discussion about, for example, a joint mission involving one satellite or multiple satellites for these services that I'll outline. In our project then, what we're trying to do is to, first of all, look at the communication architectures and the particular waveforms and the protocols, with an emphasis on new techniques for getting much higher capacity than has previously been obtained. we have got a Phase A study which is looking at orbits and other things to do with the hardware that you would use, the electronics that you use in space. In a little while I'll talk about a trial that we'll be conducting quite shortly to prove this concept, which involves a surrogate satellite, an aeroplane, which is provided by our DSTO partner. And we're very actively looking at possibilities to get the system into space once that we've actually proved the concept with the trials and the simulations. And we'd hope eventually that there'd be a constellation of satellites, although it's very feasible just to have a single satellite initially as a demonstrator which could provide useful results from the systems that we've designed. Just to look at the concept here, on the Earth's surface in remote areas that haven't got existing communications infrastructure, we will have sensors either individually or in small networks. We might have a small terrestrial network which can upload data to the satellite when it comes over, a LEO satellite. Now, I've talked about uploading and collecting data, but in addition there's some instances where you want to have bidirectional links, and I think I'll go into that on the next slide. It's likely that the satellite would not be in sight of a ground station when it's over these remote areas. It may or may not be, and so later in the orbit it will need to communicate efficiently with the ground station, or sometimes it will need to do both at the same time, being able to see the remote areas, terminals in remote locations and ground stations as well. That basically is the concept. What we call the two service types that we've looked at is first of all, uplink only, so unidirectional. So as I said before, tens of thousands of sensors in the field of view, up to 100,000 sensors in the field of view of the satellite, with very short messages. For example, sort of messages you could envisage would be the location of, well, those goats, for example, or lots of other objects. The other type of terminal will require bidirectional links. So if you've got longer messages and if you want to receive some sort of acknowledgement that your message has got through, or if you would like to command the terminals to operate in some different mode, or for example if you'd like to do things like software upgrades or firmware upgrades. So it may be point-to-point, or more likely it might be multicast. You might be wanting to download the same update to a large number of terminals. So we've tried to cater for these things in a flexible way. The flexible manner means that sometimes you may want to have a system with a very large number of terminals with short message lengths in the bidirectional scheme, or sometimes a smaller number of terminals with longer message lengths. So this is where the software-defined radio comes in to make that work. So a central part of our approach has been to develop new methods of providing the very large number of terminals, given that we already have some existing satellite systems that can do this with small numbers of terminals. There's been a lot of effort in this particular area of the project, and together with that we've designed a realistic network architecture and a set of protocols that will work all the way through the stack to make this feasible. Let me give you a brief illustration of the type of processing that we're talking about. So here we're looking at a realistic simulation of a scenario where we have many signals which are crowded together and sitting on top of one another in the time frequency plane. So the horizontal axis here is the frequency domain, and this is the time domain, and the vertical direction is the power domain, and or amplitude, and colour represents power. So we have got an algorithm which addresses these signals one by one, and as it steps through the processing, you can see that we are removing areas of signal, of received signal, and as we do that, we expose the underlying signals. As I go through this process, at the top of the screen, you can see that we've got green ticks appearing, which are markers that indicate those signals have been successfully removed. We get to the point where, well, there's only one signal left there, so compared to the plot at the bottom, we've actually removed all of the signal components, and this is one of the key ways that we can handle many signals that sit on top of each other and get that high capacity that I spoke about. If you're a communications person, you might recognise that the removal of these signals is not completely perfect. There's actually a little area down here where there's a little bit of residual signal left over, but in fact it's good enough that we've been able to demodulate all of the packets that were received that were sitting on top of each other. That's an example from a simulation result. So we've had to do a lot of design and simulation of these systems, but we're not limited to that. The result that I've got here is a similar type of illustration, but this has actually been demonstrated in real time in Canada using a space qualified front end in ComDev. So on the left hand side we have what's called a spectrum, and you can see the power distribution versus frequency of two signals which are almost sitting directly on top of each other. On the right hand side we can see again the picture of the signals in the time frequency plane, showing how the cancellation process has actually demodulated both of those packets successfully and left us with a little bit more residual than we saw in the last one, but it's worked. Right, so the current status of this project is that we've surveyed user groups and we've worked out the requirements, and we've done quite an extensive survey as part of that Phase A study. We've developed a lot of innovative approaches to doing this. We've simulated them, done a fair bit of analysis. There's a lot of IP that's being produced, quite a lot of that's being protected by patenting procedures. We've gone through real-time implementations, some of which, well, wherever we can, we're actually trying to test it in a realistic fashion on real space hardware. The trial that we have coming up in the next couple of months is a very important part of our project, where we want to actually prove this concept in as realistic a way as we can. I've said here that we've got a satellite surrogate. In fact, we're also wanting to use real satellites in this trial, but in a data recording capacity. And so as this plane, which is simulating the satellite, will be flying around in the South Australian area, at the same time we'll be collecting signals from space, but there'll be real-time equipment on the plane which will be mimicking the operation of a processing payload. We need to have a real-time implementation so that we can illustrate those bidirectional protocols working that I talked about. There'll be a bunch of terminals on the ground in various parts of South Australia. There'll be terminals in the water, in buoys. There'll be terminals on the land. They'll be measuring various parameters of environmental parameters. There'll be positioning involved, and as I said, there'll be both real-time and non-real-time processing on the plane itself and on the ground terminals. There's a lot of effort here devoted just to calibration. to get useful results out of this. It's an effort to, it's quite a challenge to actually calibrate this in a way because of the differences of the environment, the airborne environment, the link budgets and so on, differences compared to the satellite trajectory. This is quite a task. Anyway, that is coming up. Just to finish off, okay, we've done the Phase A study involving all the normal things. I'll skip over that. By the mid this year, we need to be basically ready for a flight program. We've done our Phase A study. We've looked at these architectures. We've done this realistic trial. And we're ready to implement the system. The next step would be to look at ways of getting this into a real serviceable system. The aim would be to leverage the total funding in the project of 12 million or so, including all the partner funds. And there are a number of discussions going on at the moment to try to look at ways that we could take our verified or our design system where we've verified what the performance will be and actually get that into space. Thank you.
Thanks, Bill. Professor Martin Westwell is Director of the Flinders Centre for Science and Education in the 21st Century at Flinders University. He has a PhD degree from Cambridge University and he's worked at Oxford University as a research fellow in biological and medical sciences, and at Lincoln College while at Oxford he undertook a number of research projects. He's worked in industry, in the biotechnology industry, and he's went back to academia again, ending up here in Adelaide in 2007. He's won a number of awards, particularly for his science communication. He brings a scientist view to learning, science education, policy and industry engagement, and he was the Times newspaper Scientist of the New Century in 1999. Martin.
Thank you. I want to give you a quick overview of our project. Our project was an education project in the education stream, and we were lucky that when the funding came through from the ASRP, we had this perfect storm going on in Australia. So we had the funding, so that was a good start, but we'd also seen that some indications that Earth observation was going to be a priority, something that we were going to really focus on in Australia. We also got a new national curriculum for school education in Australia. And it was world-leading in many ways. In science, we've got this whole third of the curriculum that's about science as a human endeavour. And that creates lots of opportunity to be creative and to do some really interesting things within education that we've not really been able to do before. And similarly, in our SACE, which is the certificate, the education certificate that our school leavers do just before they leave school and go on to university, we had this thing, a research project, a space that had been created in those senior secondary years to actually do some research, really founded on strong educational principles. And, you know, if it had been up to me, we'd have done nothing in year 12 other than research. You know, for that STEM pathways, you know, I'd like to see more of that actual thinking and wielding knowledge effectively in year 12. So all that came together for us, and so we tried to package that up and make the most of that in terms of our project. And what I'm going to do is I'm actually going to for the first 2 minutes, a children's TV show, Totally Wild, that shows here in Australia, tell you about our project.
Imagine this. You complete a school science project and the data you collect will be used in research for restoring the environment. These students have a special advantage over their peers though. They get help collecting their data from a satellite-enabled research plane. So this is the plane you guys use. Talk to me about all of the equipment necessary to get all that data in storage.
Okay, well, you can have certain different lenses. This is a thermal image lens, and here you can see your face is white, so that means it's really quite hot. Also, you can get another lens. It measures how much chlorophyll is found, say, in plants and grass. It makes it green.
And then there's also the LiDAR scanner, and that takes a one-line image of what the plane's flying over, and that gives a really high resolution.
Bob Buxton is the Project 21 officer, and he oversees the whole operation. He works with the students and the university, bringing together all the data that is collected.
All this data is available for other researchers to use for whatever purposes they like. This particular data set is being used by the Urban Heat Island Research Group at Flinders University, looking at the different effects that you get from heating of urban areas compared to other outside areas. Other government departments, other research groups, it doesn't matter which sector they're from, are freely available to have this data, and some do use it.
So what research are you guys doing specifically?
Well, I'm looking at how many solar panels we'll need for my school to generate all electricity.
And I'm looking at which colour is the most thermally efficient, because some roof colours reflect or absorb heat better than others.
Okay, and how do you guys pick these topics? They seem pretty, interesting and unique.
Well, we're working with Flinders University, and they sort of gave us a basic guide, but we get to choose what data we want, and then they send it back to us.
From the outside, these technologies seem pretty simple. Most of us have heard of cameras and satellites, but the real heart of this project is its future implications. What do you guys see resulting from all of your research?
I'm hoping that companies realise that colour helps thermal efficiency of houses, and that they'll educate the customers to make a good choice.
Well, I hope that my school will implement some of my research done, maybe get 50 solar panels for our school. I consciously do think about the environment, so hopefully this will help. Maybe other schools might implement what I've done as well.
These guys are youth scientists. They utilise modern technology to save the environment and, of course, to get good grades.
So you can see that, the language that you used was naive, and probably not the kind of correct sort of language that we'd be looking for. But I think you can also see in there that they were living it. They were using the instruments in which these research aircraft at Flinders University could be equipped with. They were choosing the instruments, they were choosing where the aircraft were flying, they were choosing what kind of data they wanted to get to address the issue that they were interested in. And so, very briefly, our project was really about, actually putting research and space research, in this case Earth observation research, into the research project in South Australia, to give students a way of using the space science and the technology to work on an issue that was interesting to them. One of the things that we see in education is, in this room, one of the reasons why we're here is because we're space tragics, right? Because space is our thing. And it turns out that when you look at the whole population of school students, they're not necessarily space tragics. And so what you get is lots of education programs that are pitched at students who are already interested in space. And what you get from that is, yes, that's great, and for those students you help to develop them and bring them on. But we're not really making our community case for space by doing that. Our community case for space actually comes from engaging a much bigger group of people, taking their issues, the things that they're interested in this case is lots of environmental issues, and using the space technology, using the Earth observation technology, for who they are, to take who they are and what they're interested in, and so that the technology can help to drive that and help them to access some answers and help them to think about and to research in and do some authentic research in things that they're already interested in, rather than trying to spoon feed and push space technology at them in an education context. So we wanted to make sure that research was authentic and that in many cases it could influence decision making in South Australia, so that the students themselves, these 16, sometimes 17 and 18-year-olds, could actually use the research that they were doing to influence other research and to influence some decision making at one level or another. And then finally, we wanted to make this community case for space to allow our students to really see themselves and to see the state growing in terms of its role in space technology. And that, I just mentioned Georgie there, that's a note for me, just to say that the dark-haired student that you saw, Georgie's going on to be a teacher. So she's not going to go on and follow the pathway to, necessarily being a professional within a space-related industry, but she's going on in education, so we kind of get that amplification effect, because she's seen herself, she's been a researcher in space technology, at a low level, but she's been that researcher, and she can take that through into her education career as well. So that's what the project's for, the people who've been involved. We've had a fantastic group of people involved. And I think that certainly for our project, that ability to draw in lots of partners has been really important. So we've got Flinders University, the university where I am. My colleague Alice Gorman, who's been involved in the project, is here as well. And Airborne Research Australia, the group who are flying the aircraft, part of Flinders University as well. The South Australian Museum, Education Services Australia, and our own state Department of Education. And Concept to Creation is an industry education group here in South Australia. Those are the people involved in our consortium. Importantly, what we got the government involved, we got all kinds of providers involved, and so we've actually made links out to lots of different people. We also, though they weren't part of our consortium, have worked with the European Space Agency, the ESRIN Centre in Rome, the Earth Observation Centre. They've been fantastic in supporting us in terms of some of the education materials as well. So we had a view of how this was going to work out, and of course in education it never works out in the way that you think it's going to, especially if it's creative and innovative. And so we set out a process where we created an electronic directory of issues and we defined the research question and so on, and you can follow that through. But of course what we found was that it was important to give the flexibility to the students. Lots of the students picked and chose from this pathway. Some went all the way through, some didn't, some did bits and pieces. The social networking tools were important because that got that intellectual banter going between students. And that was really important to this project, I think. I'm not going to walk through that process. But what we certainly did find was that, in education, what we're finding is that, traditionally in education, what we think about as being learning is actually what can be taught. It's the things that can be instructed. And if you were born in the 1950s, that was enough. In fact, what would predict your earning power in your 30s if you were born in the 50s was your school literacy and numeracy. And that was pretty much it. For the kids who were born in the 70s, what we found is literacy and numeracy was still really important. But now we got things like application, your ability to complete complex tasks and to approach complex tasks, your locus of control, the extent to which you think your education and the work that you're doing is within your control, you've got some influence over it. Those things were actually bigger predictors of your earning power at 30 than your literacy if you were born in the 1970s. And so what we've seen is that the world's changed, and that instructable component of education is getting smaller and smaller and smaller. But what students can learn is getting bigger and bigger. And so this project, while the structure may not have worked out exactly as we wanted to for lots of students, what we made sure was we held on to the principle that while we gave some of the control back to the students, we knew what we wanted them to learn, we knew we wanted them to develop an identity as a researcher within space science. And I think that's what we got out of it. I won't talk too much about that. We also found that to help students to not engage with this project at a facile level, just to look at it as a knowledge project, as an information project, but actually to get stuck in, they needed some support in terms of scaffolding and project planning. That was one of the things that was stopping them from delving in because they didn't really know how to approach project planning. So we actually generated an electronic tool because we saw that lots of the teachers didn't necessarily have project planning skills. And so we created this online tool to support student project planning so they could really dig in deeply. We also found that what was going on in the schools was that the research project was being facilitated not by scientists, not by technology teachers, but actually a great deal by teacher librarians and people like that who didn't have the science and engineering background. And so we've actually provided professional learning through this project for teachers who are teaching research education to bring in space science, to bring in science, technology, engineering and maths to their projects. And so that's been really important to us, to be responsive to identify where the gaps are, to identify where we can move and intervene and where support's needed, and to move into those places and to support students and their teachers. And by the end of this semester, so in the middle of this coming year, depending on how the uptake goes in this next semester, we'll have had a couple of hundred teachers go through that professional learning process. So for us, our successes so far have been that we've had about 2,000 students in South Australia engage with space science in one way or another through this project. So they've attended our workshops, they've attended some of our information sessions. We've had so far around about 300 students spend a whole day workshop down at the hangar that you saw on the video clip at Airborne Research Australia, looking at the instrumentation, engaging with the instrumentation that's available to them to do the project. And they've gone off in all kinds of different directions with that. Some students went off and did some design of their own instrumentation, some students went off in other directions. And so far, about 40 students have actually gone down the path that we imagined, where they started at the beginning and they worked through that process to develop a semester-long project. For us, coming to the end of the funding, our legacy planning is really important to us, and of course now what we're thinking about is how do we make sure that these resources that we've built through this project, the data that we've collected, the research education principles that we've put in place are going to carry on having an impact. And we're working with the South Australian Government and our local South Australian Museum to develop those materials and to make sure that those materials are updated and that we can continue to provide professional learning for educators around those materials. We're also going to be producing in the South Australian Museum an augmented reality exhibit, and so we can use augmented reality to overlay data, to overlay Earth observation data on a whole host of surfaces so that students can take their data, can manipulate their data and actually apply it to these augmented reality surfaces in the South Australian Museum. So a really quick overview of our project, but for us the really important things have been the principles, that this shift in education that's occurring from this kind of industrial model of education to this post-industrial model, where research education has got a real place, not just in postgraduate, not in undergraduate, but actually in school, science, technology, engineering and maths. That's been a real, if we look at that shift globally, for me that's a real point in which space education can really get into classrooms, can really make a difference, because that innovation and creativity that comes with space science education can now be expressed in schools in ways in which they've never been able to be expressed before. Thanks very much.
And the last speaker this evening is Andrew Clark, who received a Bachelor of Engineering degree from Adelaide University and then spent 11 years in the United Kingdom working on satellite systems and aircraft structures, returning to Adelaide to Vipac Engineers and Scientists in 1993. He's worked with CSIRO to develop an atmospheric pressure sensor, which was the precursor to the greenhouse gas monitor, and he's now the manager of the Greenhouse Gas Monitor program that's funded by the ASRP. Andrew.
Thank you very much. We're a little bit different because we're a private company, and all we're doing is developing an instrument. It's quite expensive to develop. It's about a $6 million program, and we've only got 5 months to go and we haven't finished yet, so that's a problem. But we're looking for more money, which is typical of private companies. The team is quite stellar, to be honest. We're headed up, but we're supported by the University of Wollongong in particular, who have a lot of instrumentation that help us. The University of Melbourne, who do a significant part of it. The Bureau of Meteorology, I'll explain their role a bit later. ANU, RSAA as well, are doing terrific work with us and helping develop optics for us as part of this. And Rosebank Engineering, who do specialist manufacture for us. So it's a fairly strong team. So what do? We're developing a novel instrument to measure greenhouse gases, mainly CO2 and methane in the column of air. I use that word because it's a column measuring instrument, which is as opposed to an in situ measuring instrument. And I've got these wonderful graphics I spent hours developing. If you look at the screen, that's what it does. Sunlight. I do that, and you laugh, but I've given this talk before, and a number of times people have said, well, how powerful is the laser that you use to get the sunlight? And there just isn't one. It's entirely passive. As opposed to an in situ device, if you look at the screen again, which sucks air in and analyses it. So that's the difference between the two. There are other ways of doing in situ devices, but the point about the in situ devices is they're fairly local and at the surface, whereas we look at the whole column of atmosphere between here and the sun, which gives you a different measurement and which has different uses. The second part of what we're doing is developing atmospheric models to take those measurements, as well as in situ measurements and overflights by aircraft and flux towers and all the traditional ways of measuring these things, and then making sense of it to look at how the carbon dioxide and methane is transported through the air, through a region, where it comes from, where it goes. So attribution of source and sink, as we call it. And that's just as important. What's the space link to all this? Well, I'll put a satellite up there. You saw before that the sunlight falls on our instrument. Well, with a satellite, it works very similarly, except it bounces back up with the satellite. So we intercept it halfway, if you like. So the technology we use to understand the measurement as it comes through and process it is very similar to what's used with the satellite. So the point of that is we can then calibrate the satellite instrument measurement, which is necessary because every measurement it takes, it's affected by the atmosphere, aerosols, dust, water vapour and so on. And you need to calibrate that out. And by measuring at the ground in a coincident measurement, you can do that. And without that, you can be out by many percent. Satellite is much more difficult because the signal is much weaker and it gets diffused by the Earth and so on. So by the time it gets back up to the satellite, you're literally counting photons that hit the detector, and the detectors can be $250,000 or more, whereas our detector costs about $2.50 because we've got plenty of photons. So how does this work? This is new. I've never presented this bit before, but we start off with a field. The field could be 300 kilometres or it could be a few kilometres. And in that field we want a source. So that's, if you like, a chimney. You're looking straight down at a chimney. You can see the flames in the middle of it there. And then, we've actually done this for real. Then we sprinkle a few instruments about, greenhouse gas instruments. And then we wait for the wind to blow. And I have trouble with this next animation. A plume just went the wrong way, but that's all right. So basically we put enough instruments around the source, which is not very many as it turns out, wait for the wind to blow, the source blows the gases, and this is a point source as we call it, so it's more difficult than most. And then we wait for it to go between us and the sunlight falls on our instrument, and from that we look at the spectrum of the sunlight as it hits our instrument, and there'll be absorption due to various gases that the sunlight's passed through, including carbon dioxide and methane. And by careful analysis of that, we can determine how many molecules are there. And with the modelling, we can then backtrack and tell you what the emission was from that chimney, which is quite remarkable. And I'll talk a little bit more about that later. So we have done a trial up at Port Augusta. There's a power station up there at Alinta, run by Alinta, and their aim was to detect the plume from the power station and then backtrack to what the emission was. And this was, we did this last May, quite a while ago now, with only one instrument. So we wanted to get in the field to see if it worked. We could have spent longer developing it in the laboratory and on the bench, but it was a lot quicker. What we learned from going out to the field was it shortened our program by 12 months. It would have taken us ages to get there without doing this. So we bit the bullet, went out to the field. We actually trialled two technologies. The Brooker IR infrared Fourier transform spectrometer, or the Cube as we call it. It's sort of an off-the-shelf instrument which we had to adapt to do this work, which we did. We adapted it internally and externally. But we're also developing our own brand new technology called a Fibre Fabric Pro Interferometer, or FFPI, which is entirely new, using an instrument which is about the size of about a centimetre long, which does the same job. And quite remarkably, we're almost about to announce it works. We need a bit more sunlight. So we had both of these up there. We didn't expect the FFPI to work because that was still very much a fledgling instrument. We actually did get some measurements from it. But the Brooker Cube worked quite well. Just some photographs. We had an in situ device as well, which meant we had to have a 10 metre tower rather, which sucked the air in off so we didn't get too much dust. The Brooker Cube itself is just sitting there on a table. We had a heliostat, which is basically a moving mirror which points a light beam at a constant spot all day to feed the Brooker Cube. And our FFPI, we just had a solar tracker which separated the light, and then using a fibre optic cable we could sit in relative air-conditioned comfort in the swimming centre at Port Augusta. Initial results from the modelling. This is the results from the Brooker Cube shown in red. And this shows the enhancement or the increase in CO2 over the background measurement each day. This is I think the 7th of May and so on. The modelling is shown in green, which we used to see if we could predict that. Don't worry about that; they don't overlap. The modelling is normalised, so the scale is not particularly relevant, but we were able to predict pretty much, just with the mathematical model, what we would have expected from an instrument, and it lines up extremely well. Very, very encouraging results from one instrument. The in situ measurements, so we took, I'm showing this for a reason, we had an in situ device downwind where the Brooker Cube was, and upwind to get a background. The red is downwind and the black and the blue is upwind, so you can see that that sort of confirms that what we're seeing is the plume from the stack. Incidentally, this enhancement here is due to a bushfire in the Werribee forest that occurred in the last day, which mucked all our results up, unfortunately, so we stopped at that point. And modelling that as well, using a slightly different model, we were able to come up with, again, this was a first cut, and it's actually quite remarkable. Again, the blue is the measurement, and the magenta is a mathematical model, and we're able to pick out each event. Don't worry about these scales so much, but no one's actually done this before. This is actually new work which is publishable later this year to show that we can actually pretty well get these measurements reasonably well, and from that we should be able to backtrack to what the emission was from the chimney. It's important, and this is something we've learned, it's important to realise that you'll never measure, so you'll never model to the exact second what's going to happen or to the exact centimetre. So you need a statistical approach, and coming up with those algorithms to give us something that's reasonable has been a large learning part of our program. I'm not sure how of interest this is, but this is the instrument we're developing. Gives you some indication why it is so difficult. But the sun comes into a solar tracker. The solar tracker is off the shelf, too expensive because we have a cost budget, a break point we want to keep this instrument down to. So we developed our own, which is, you think it's known technology, but we have to look at the centre of the sun, the centre kernel of the sun, to an accuracy of 0.001 degree. The reason for that is if the sun is spinning, if you look at one side or the other, you get a Doppler effect, which affects your signal, and you can't retrieve CO2 or methane from the signal. So that's how accurate you need to be. We then go through some four optics, which are new, helping us to develop. The interferometer itself, which is about a centimetre long, and then some electronics, a detector and some electronics to get it into a computer. The idea is that we then wirelessly transmit it to a data management centre. As I'll explain in a minute, we also need meteorology to understand where the plume travels, so we can then backtrack to where it came from. A lot of software to be done. All this is in real time. And there have been several spin-off technologies that we didn't expect out of all this. Low noise. Noise is a problem. We're trying to pick up 1 part in 400. There's about 400 parts per million of CO2 in the atmosphere. We're trying to get it down to pick out less than 1. And to do that with remote sensing is quite remarkable and almost unheard of. So we need to be highly accurate. So any noise, thermal noise, shock noise, a whole range of different noises I've never heard of before is affecting us. And that's forced us to develop all our own electronics almost all the way through, including the solar tracker right through to the detector, which we're developing ourselves as well. And there are some spin-off technologies which are of value out of that, which we hadn't anticipated. As well as the software algorithms to interpret all this stuff, we needed our own software. So there's nothing off the shelf. We've had to write all that ourselves, and that's effectively done and mature now. So I said we did take the FFPI up there, and this is the first spectrum we received, we measured. It looks, well, it doesn't look too bad if you don't know what you're looking at, but these are absorption lines. If there was no atmosphere and the sun has an atmosphere as well, if either the sun or the earth didn't have an atmosphere, the energy spectrum would be a straight line across the graph. This is frequency or wavelength, if you like, along the bottom. As it passes through the atmosphere, you get these dips in energy, and that means that some of that energy has been absorbed in the atmosphere, and there's a characteristic fingerprint of the molecule that has done the absorption, and several of those are CO2 in that graph. A lot of them are water. Water's everywhere. It's not good enough at this point. It's still too noisy at the top. There's a lot of squiggles up here. The red is the observation. So we have smoothed that out now. In fact, we're almost at the point. As I say, we just need sunlight to do one final experiment to confirm that we can get down to 1 part per million. From that spectrum, which was back in May, we're lucky to get 10 parts per million. So we've come in by a factor of 10 over the last 10 months. So once we know that, how do we backtrack to get what's coming out of the chimney? As I say, we have what we call a grid, which could be, typically starts about 200 kilometres across, a square grid, and then on that grid you put in forcing meteorology. So on that box you work out what the meteorology is, what you've measured. Well, it comes from the Bureau of Meteorology. There's other places around the world that provide it for you over time, over your observation period. And that becomes your boundary conditions for your analysis. Then you go inside and do your own analysis. You go to smaller and smaller nested grids, right down to, we've gone down to sub 300 metres. In fact, we're going down to about 30 metres. And using fluid dynamics and understanding the wind fields all the way through there, we can predict the wind by doing this for the whole 2 weeks we're in Port Augusta. And by knowing the characteristics of the plume coming out of the stack, we can then predict whether the stack's going to be pretty much within half an hour, and that's good enough. And from that, we can then, with a single observation point or a few observation points, we can then backtrack, do an inversion model to come back to what comes out of the chimney. We're within 5% of the chimney, the actual emissions, but we hope to improve on that. So the long shot of this. The upshot of all this is what will we produce out of this if it all works and we get it to fruition. Flux maps, carbon flux maps. The chart on the right there is about the state of the art, a few hundred kilometres across, which is studies that were done not using column measurements but using in situ devices and aircraft, looking at a flux map as the transport of carbon over time over a region. And the best we can do at the moment is about 300 kilometres across. We haven't done much better than that. The middle chart shows the only satellite that's up there doing this now is GOSAT, a Japanese satellite, and that's the sort of resolution you get. In its way, it's very good, but it's uncalibrated because there's no way of ground truthing or calibration from the ground from it. And again, it's very, very coarse. There's a lot of other satellite instruments in planning. OCO2 will be launched, I believe, next year, 2014. $250 million, and it's an experimental instrument to do the same thing, but it's coming. There's several others on the drawing board. Another one of the spin-offs is managing that data. The satellite does daily overpasses. You've got to be able to process that data every day, otherwise you get behind. You never catch up. So we've been developing new algorithms to speed up the traditional way of doing it for specific to CO2 and methane, which again is world leading at the moment. And there's a program called GeoCarb being run by Lockheed, which is still on the drawing board, but they're talking to us very seriously about taking over the data management services, which will require a supercomputer. But they're not as super as they used to be. You can get a 10,000 core computer for not much money these days. It'll fit in a few racks. So it's becoming doable. And of course, the other thing we'll do is produce the instruments themselves. I'll go through this pretty quickly. The things we've done so far in the ASRP program, we've developed 2 instruments. We've done several trials. At Wollongong, They have what's called the gold standard instrument there, called a TCON, the Total Carbon Column Observing Network Fourier Transform Spectrometer, but no one ever says that, which is about a $700,000 machine that requires a dedicated scientist or two to run it. We're hoping to do something that does the same job for just methane and CO2 for a tenth or a 20th of that cost. But we're using TCON as a calibration standard, so we're matching that with our technology. We did a field trial in Port Augusta in May, ongoing trials here at Vipac in Kent Town and at Wollongong, and we're planning to go back in the field again in April or May this year. And the modelling side, as I say, that's been lagging along a little bit because we didn't have the data, but we're starting to get really good results there, and we're now leading the world in that field as well. The applications for this, the federal government kindly brought in the Clean Energy Act, which created a market for us. Ways of measuring remotely emissions that were difficult or expensive to measure before. With our instruments, we now have a market for doing that, from some single stacks or from multiple stacks and so on, landfill and so on. The top 20 polluters are each paying bills of $100 million or more in their emissions. Monitoring them over time from mines, water treatment sites, landfill sites, regional councils, economic regions and so on is now possible, which it was just too expensive before or impractical. What is new, something that cannot be done at the moment, is monitoring sinks. There's no easy way to monitor a sink from a large area. You can have an in situ device and measure the drawdown in the atmosphere of carbon dioxide as the plant grows, but you can only do it at a local area, and you've got to infer it over a large region. We can surround a large crop, and as the wind blows over, we use the wind to integrate what's happening, and we can see the drawdown over time, and this has been done using this TCON instrument. And by knowing the biomass, you subtract off that from what your drawdown is, and what's left is what must be in the soil. So what goes into the crop and what goes into the soil is we now have a much better handle on measuring. It still won't be accurate, but it's far more accurate than the current methods. Carbon accounting. The Australian government's putting a lot of money in carbon accounting. There's a lot of requirements from the Kyoto Protocol. And there's programs north of Australia looking at using forests to capture carbon and so on. It's mainly done by satellite measurements of looking how many trees there are and counting them up. We offer a way to do an actual measurement to validate all that. I said the Bureau of Meteorology are involved. When they do their daily weather forecast, they have one number which comes out of America of the estimate of CO2 in the atmosphere in Australia across the whole continent. If we can provide a sprinkling of these instruments across Australia, we can do a carbon flux map daily of CO2 and give a more accurate estimate of that. The reason that's important is that it gives them a better handle on the starting temperature when they do they run their models to get a forecast. So with a better knowledge of their temperature, they're expecting, and they've done models to show this, that they'll get a better weather forecast. How you measure how better it is very difficult, it's very subjective, but that's the reason they're involved, and we're funding a postdoc there to do just that, and we're doing those simulations at the moment to see how improved the forecast will be. And last but not least, and no one's ever interested in this because it doesn't make money, is we have a better understanding of carbon cycle science, which is probably the most important thing out of all of this. A better understanding, especially of what goes into the sea, which is poorly understood and is critical to any global warming debate. I'll go this very quickly. The market is big, which is why we're interested in this. The World Bank report at the end of 2011, there's another one's about to come out. The global carbon market is worth over $150 billion. We estimate the lower bound of uncertainty in that is at 3%. It's probably more, but that's greater than $5 billion for the atmospheric carbon. And in the soil, it's 10 times that or more. So as the market, as Australia enters that market, greater knowledge of reducing that uncertainty it could well be worth a lot of money. We hope so. Opportunities will be coming up. We're planning in the next 2 years. So we have, even though the money will stop, Vipac will fund further research, and we're looking for other sources as well. Going back to Port Augusta, we want to set up that's the Port Augusta power plant. We want a calibrated test site there so that we have a whole bunch of instruments, and every time we build an instrument, we can calibrate it there. And then we want to link a satellite overpass from GoSat and the other ones that come on stream to what's coming out of the chimney at Port Augusta. That's important because if we can show that link is reliable, the satellite that flows over us then flies over China. And we can do the same thing to estimate what's coming out of Chinese and other power stations, which is of interest to national security people, interest for Kyoto validation, verification. So there's a lot of interest in getting this technology to work and demonstrating it can work. Multiple sources, more of interest to how much people emit and how much it costs them and so on. Difficult to measure a lot of these things. Often, if there's not an instrument inside the chimney itself, these things are monitored by or measured by the bulk input that goes in at one end, and they do a calculation, and so must be CO2 coming out the other end. Highly inaccurate, easily distorted. We can set up downwind and just measure it. Hopefully that'll reduce some of the uncertainty in that. Diffuse source, very difficult to measure. That's the Werribee treatment plant, just west of Melbourne. West of Melbourne. Methane, NO2, comes off of that. Very difficult to measure again. They take samples every now and again with an in-situ device and do a calculation. They don't even know how accurate that is, but it costs them a lot of money. Their bill's about $5 million a year in tax, and it could be half that, it could be double that. They just don't know. A hot topic, literally. Fracking operations, coal seam gas emissions, very difficult to measure because you don't know where it's going to come out, and very expensive when you've got a large number of potential sources. We can step back 10, 20 kilometres and just measure the whole field and get an idea of what the emissions are. Very emotive. Farmers are upset about it. They're saying one thing, the miners are saying others. Both agree you need more information. This gives us an opportunity to do that, hopefully. And as I said, sinks. Next spring, the growing season, where you've got the best chance of measuring stuff, we're looking for the ideal crop that will grow quickly, that will give us the greatest drawdown. We hope to be in the field probably August, September next year for a few months. The sink field trials are expensive because you have to be there a long time. You want the before, during, and the after, so you know you've got the during. So you need the background before and after. So we hope to be ready to go in the field next spring to do that, and that'll be a world first as well. So what do we hope to do with all this? I'm running out of time. Yes. GGM has been designed to be networkable, so totally autonomous, so you can put them in the field anywhere, self-powered, wireless technology back to a database, could be here, anywhere in the world, and you can cluster them and you can move them. That's new. We're also looking next at an airborne instrument. There's a good economic case for an airborne instrument, not so much for a space instrument, but that could easily come on for a low-cost space instrument, and of course ongoing research. And that's it. Thank you.
Okay, we've seen, I think, some really cool technology. We've seen some fantastic science. We've seen some brilliant infrastructure, enthusiastic kids. It's kind of the ASRP Christmas. But I did promise you questions, and I did promise you drinks, and we're just about the point in time where we're going to have to compromise here. So I'll throw it open for a couple of questions, and then we can continue the conversation over drinks with the panellists. So are there any burning questions people would like to ask now? I think Chrissy's got a microphone at the back. There's one right down here. Walk the long way round.
My question is for Harvey. Harvey, just with those ground tracking stations for space debris, how many of them are there worldwide, and how many in the Southern Hemisphere?
Well, there's two in Australia. Both of them run by US-based systems. There's a whole lot of military ones that we don't know how many there are. There are programs in the civilian world from NASA and ETA. I imagine JAXA's probably also involved. What Australia has, what the EOS guys have, is a much more accurate way of measuring. Most of the measurements are done with microwave radar, and much more accurate to do it with lasers. So in terms of being in the market with something that's special, the US guys have really got it.
Another question? Up the back in blue.
Hi, I'm Chris Butt from a student currently at the International Space University. And Professor Martin touched on a point of contingency after sort of this ASRP funding has run out. I was just wondering if you could comment on the future of programs such as the ones that have been set up under this funding and where they can move forward to in the future without the funding.
I think that's probably one that I'll take. The reality is that this was a program that was identified to fill a gap, and as I said at the beginning, it's $40 million, right? I think if you added up all of the research funding in Australia in any given year, it comes to something like $1.7 billion worth of funding, right? So what these are doing are building teams of international and national competitiveness to be attractive within these sorts of funding pools to go into afterwards. So in the shorter term, it's the traditional funding pools, whether it's the Australian Research Council or other organisations. In the longer term, of course, sustained investment in space research is going to be needed if Australia is serious about actually delivering the outcomes of some of these projects. And while some of them will have commercially derived benefits and will get investment, others which are more scientifically based are going to need funding from elsewhere. So we're not sure whether there'll be another ASRP tranche of funding. We hope that there might be, but if there isn't, what it's done at least is created cohorts of researchers, consortia of people who are able to deliver the sorts of, demonstrate that they can deliver the outcomes that can source funding nationally and internationally. All right, so I'll call it a day there. We can go and have some drinks and continue to talk about the programs themselves. Can I thank with you all the panellists for their presentations and wish them well with the future of the projects.